and I simply couldn't understand what it was.
Oh,
But
okay.
I just kept looking at it, and I used to skip some things and go forward and see whether I could understand that. And that was not the correct approach. But that definitely got me involved. And also, I learned how to study things by myself. When I said that I would like to go to Bombay because I want to do science, I want to do research, I did not know
Mm,
what the meaning of all those things.
okay.
Then our relatives, of course, were not very happy about it. They said, become a doctor, become an engineer. And if you don't want to do that, just get an MSc here and become a teacher. My parents said that, look, you can go wherever you want and you can do whatever you like. And they
Mm,
trusted me completely. I went there and then I looked around and I saw the sea and I saw the library and I said, this is my place. I'm going to be here.
uh,
So I started going to TIFR when I was exactly 18 years old. I decided not to study at all for the exam. Okay. And so because I was just trying, how well can I do by doing my worst? In Einstein's theory, what happens is that if there's a singularity in the matter density, because everything is packed at one point, it will mean also there'll be a singularity in the space-time structure. And that is very disastrous. So now the question is whether this singularity is real, meaning is it unavoidable, or if the singularity has come simply because there is homogeneity and isotropy.
Hello and welcome to Intellectual Rigor. I'm your host Mehul Desai. Our mission on this channel is to delve into the lives and minds of brilliant individuals who have shaped science and mathematics. Today, we have the distinct honor of hosting a pioneering astrophysicist, an institutional builder, and a mentor to generations of scientists in India, Professor Ajit Kembhavi. Professor Kembhavi is a professor emeritus at the University Center for Astronomy and Astrophysics, or IUCAA, in Pune, an institution he helped build from its very inception and later led as its director. Professor Kembhavi, thank you so much for joining us on My Life in Science. Professor Kembhavi, warm welcome to you. I'm truly delighted and honored to have you with us today on Intellectual Rigor for our My Life in Science series. On behalf of our entire audience, thank you so much for taking the time to share your journey with us. We are grateful for this opportunity. Could you paint a picture for us of your childhood in Hubli during the 90s? What was the atmosphere at home and in the city like back then?
See, Hubli is a very normal, ordinary kind of city.
Hmm.
In those days, it used to be quite pretty.
Hmm.
I stayed with my grandparents because my parents used to be in other places.
Hmm.
My very early schooling, the first couple of years was in Hubli. It
Oh.
was not well defined because I was here and there. And
Mm.
then I joined my parents when my father was transferred to Bangalore, where I had my schooling up to the first half of the sixth standard. And then I shifted to Hubli again. And I was there until what is now the 12th standard. So that was 6 years. So four of which were in school and two were in college.
Mm.
So at that point, as I said, it was just an ordinary city.
Mm.
And they are nice people. And in my school and college, I
Mm.
was quite, let's say, encouraged to do what I liked because already I had become interested in science and I used to uh, read books, etc.
Okay.
My teachers in school were not necessarily able to answer questions which I had, but they were very appreciative of the fact that I was doing these things. And they gave me some liberties. Then, when I went to college, I was in what is called St. Mary's High School in Hubli. Then I went to PC Jabin Science College. Okay, so there, again, I very quickly met a couple of physics teachers. There was a Professor Chavdi and then Professor Madan Gopal, who was professor of chemistry. Then what happened was that they both used to ask questions, lots of questions in class, which I used to answer.
Okay.
These sometimes went beyond the studies and what
Mm.
is happening. So I quickly established a rapport with them, therefore with other teachers as well.
Mm.
And then I by then got interested in science
Mm.
seriously.
Mm.
So it was the fashion at that time. It was the start of the fashion at that time for people who could make it to
Mm.
go to engineering or medicine. In fact, the other careers were simply not there. I mean, either you did that or you just took a government job or a bank job or something like that. The other possibilities which exist in abundance were now simply not there, particularly in a small town. And one very remarkable thing was that, unlike the present day, the cities used to have, even small towns like Hubli, used to have good public libraries. And they had a particularly good one. And there are a lot of books there. And there were some books on astronomy and the Atlas of the Sky. And I used to read those, started reading those books. And then there was this books on, they're called Shom series.
Yeah, outlines. Sham's
From
outline.
60s to the 90s or so, 2000, they were very popular. And
Yeah.
they used to have, they're a sort of a thing between a textbook and more like a guidebook.
Mm.
But they had this most wonderful diagrams in a book on calculus.
Mm.
And I simply couldn't understand what it was.
Oh,
But
okay.
I just kept looking at it, and I used to skip some things and go forward and see whether I could understand that. And that was not the correct approach. But that definitely got me involved. And also, I learned how to study things by myself. And so then I decided to go to Bombay. At that time, my father used to be in the state transport,
Okay.
and he had a paralysis stroke, so he was not in the best of health.
Oh,
When I said that I would like to go to Bombay because I want to do science, I want to do research, I did not know what
mm.
the meaning of all those things.
Okay.
Then our relatives, of course, were not very happy about it. They said, become a doctor, become an engineer. And if you don't want to do that, just get an MSc here and become a teacher. My parents said that, look, you can go wherever you want and you can do whatever you like. And they
Mm.
trusted me completely. And
Mm.
then I went to Bombay.
Mm. Roya College.
Yes, I went to Bombay to Rio College, and there they were the friend of my father. And I
Mm.
did not had never heard of Rio College.
Mm.
There's some people in Bombay who are helping me to try to get admission to the colleges, but my result was not out long after the Bombay results were declared. So they were the problem. And then when the results came, then I went to a couple of colleges and they said that they will look into it. But after that, what happened was that my father's friend, who was a great engineer, he took me to Rio College because he knew the people there. And then they admitted me without too much. Because I got very good marks.
Mm.
And then also I got a place in the hostel.
Mm.
Then I had a Professor S.P. Patel, who
Mm.
was just a few years older than me. And he had just finished his MSc. And
Uh,
he was appointed a lecturer in the college.
okay.
And he started teaching us. And I very quickly met students from my class. And in
Okay.
those days, there used to be a science talent exam. And I had not known about it at all. So these people, there are three, four people who are the science talent scholarship.
Mm.
And then we all used to talk to Patel, and then he, of course, encouraged us very much. And then
Mm.
these people told me that there is a place called TIFR, where there is a professor called
Mm.
Udgaonkar, and who was the head of the theory group at the time.
Mm.
And they said that he conducts these things for students on open Saturdays. So they said I could go along with them if I liked.
Mm. Mm.
So I went there and to TIFR with them.
Mm.
It was quite far because I used to live in this hostel in Sion.
Mm.
I went there and then I looked around and I saw the sea and I saw the library and I said, this is my place. I'm going to be here.
Uh,
So I started going to TIFR when I was not yet, I just exactly 18 years old.
okay. Okay. So
Then,
in the BSc.
yes. And then I kept going there for projects. We did some projects in Ruya and then some projects in TIFR. It was very nice. Then at that time, it was considered right and proper for people like me who were interested in doing research in physics after they finished their BSc to go to IIT Kanpur or IIT Bombay for an MSc. So when I finished my BSc, I went there to IIT Kanpur and all these IITs and I got admission. So, but I decided not to go because of my fascination with TIFR and I said that I'm going to stay here. And therefore, I continued in Roya College and Bombay University Physics Department was just starting.
Okay. Okay.
And then the Professor M.C. Joshi of TIFR was appointed the head there. So we went there and Professor Arvind Kumar joined and Professor Rangwala joined. There was just a small number of students. There were only two buildings on the campus at that time. So it all went very well. And after MSc, again, the fashion would be for people to go to IIT, one of the IITs, and then apply for a PhD abroad and go there. But again, because of our fascination with TIFR, there was a friend of mine, and he and I, so we applied to all the research institutes, of course, be on the safe side.
So by the time, did you decide some specific area of astronomy, astrophysics, or
No,
broadly you
I
had
don't think so. I mean, I was interested in astronomy and astrophysics,
Hmm.
and I don't think that I read too much in it. We used to read a lot of quantum mechanics and quantum field theory and
Hmm. Hmm.
those kind of things. Yes, we went to all the research institutes and appeared for interviews. At that point, I met some people for the first time, and many of them have become my lifelong colleagues and friends. So then we wanted to enter TIFR, but it was very competitive. Even now, it is very competitive. At that time, it was super competitive because many people wanted to come. And I wanted to hedge my bets a little bit. I said, what happens if I don't get in? So I said that let me try to get into the Indian Institute of Management. That was the only one at the time. I am Ahmedabad. So I decided not to study at all for the exam. Okay. And so because I was just trying how well can I do by doing my worst or maybe in preparation.
Ah,
But there's a set a minimum condition, right? So let's see what we go without preparation. So there
hmm.
was a written test, and after that there was an interview where there were about 20 people present,
Hmm.
and there was a group discussion. And
Hmm.
after that, I got in. So
Okay.
I would have gone. I like that kind of thing also. So if I had entered IIM at the time, my trajectory would have been completely different,
Different. Yeah, of course.
right? So then when I got admission, then I wrote to them and said, "Look, is it all right if I come next year?"
Okay.
Yes, they said you're most welcome to come next year, but you'll have to pass the interview again. But by then I got into TIFR, and so I didn't think that there would be a need for me to apply unless there was a disaster in TIFR, which there was not. At that time, another interesting thing was that physics people were started doing molecular biology. There was sort of the first generation of physicists going into molecular biology. So, so when I was going around TIFR, I eventually got admission there, and then I was
Hmm.
going around asking people what to do. And so I had astronomy and astrophysics firmly in mind, and in fact, I was admitted to that group. But I also went to the molecular biology section and asked Professor Maitra whether I could do a little bit of both. And he said that you first do one thing properly, then we'll see you.
Okay.
But
Okay.
then I remembered, and I wanted to work with Professor Jayant Nalika.
Uh-huh.
And there were rumors that he was going to join TIFR, but when I joined TIFR, he was not yet there.
Okay.
So I joined Professor Srikantan. Then they sent me for this X-ray astronomy, balloon flights and things. Okay, but over the first 6 months,
Hmm.
see, the first 2 years in TIFR was spent in the graduate school. You have to take a large number of very difficult courses. So they also they said that you go for a balloon flight, and they were trying to get me interested. But then Nalika came to TIFR, joined there. So I spoke to Professor Srikantan. At that time, several of my friends wanted to change their allotted departments. There's a big problem.
Hmm.
But then Srikantan was a very fair person.
Okay.
So he said that you want to go to theoretical astrophysics, but if Radhika selects you as a
Hmm.
student, then I'll let you go. But I will not let you go. Okay,
Okay.
because there were some issues at that time, and he said that he would consider it much better for me to remain with him and go there.
Okay.
But then eventually Nalika selected me, so I joined.
Okay. And at that time, you were aware what Professor Narlikar was working, what was
Yes,
his area of research.
sort of, and I had heard about him from a very young age.
Hmm.
Then he actually gave a course on general relativity.
Hmm.
Then I attended that course, and then there were four of us competing to be with him.
Okay.
But one of those was actually already in the astrophysics group.
Hmm.
And it was decided that if he did the course properly, he would join Nalikar anyway.
Hmm.
So then the three of us left, and finally Nalikar spoke to us, and there was a question of doing well, but also of seeing what we could work on, etc. And so he took me.
Okay.
So
So as soon as you joined Professor Nalikar, what kind of problems he gave you?
Nalika was a very good supervisor and
Hmm.
very flexible.
Hmm.
What he used to do was that he used to suggest some problem to you and you worked on it. And if you didn't like it, you could do something else.
Okay.
And then if you needed a lot of help, he provided a lot of help. But if you chose to work by yourself, then he let you work by yourself.
Hmm.
And over a period of time, more students joined him. I also
Hmm.
found that there were some students who did things very independent.
Hmm.
And they worked in areas which Nalika was not very familiar with. Okay, but the other people were heavily dependent on his assistance. Sort of in between. He suggested some problems. I did one or two of those all right, but nothing very much.
Hmm.
Finally, he asked me to work on this conformal theory of gravitation,
Hmm.
looking at cosmological singularities in that theory and
Yeah.
could be got wrong. So it was all right. Okay, so I
Hmm.
I worked in that and wrote several papers. But I
Hmm.
was always interested in astronomy as so. So I worked
Hmm.
on one or two problems by myself with colleagues. There's a colleague called Vasant Kulkarni in the radio astronomy department, and then we worked on some problems and went on like that.
So could you slightly tell us about cosmological models with singularities? What did you specifically work on and explain us for our audience?
See that the standard model of the universe now, what is called the Big Bang
Hmm.
cosmology,
Hmm.
okay, in which the universe began from a Big Bang, from a point. It has the dimension of a point, and it exploded, and it was very hot at that time.
Hmm.
And then, as it expanded, it cooled, and it gradually took on its present form.
Hmm.
But the point at which it exploded from,
Hmm.
because there's so much matter, you don't know how the matter was created.
Hmm.
But at one point, because it was so dense, and
Hmm.
in fact, it had infinite density right at the beginning,
Hmm.
it would also mean that the gravitational field had a singularity. So, in Newton's theory, for example, if you've got a point particle,
Hmm.
the gravitational field should be at that particle itself.
Hmm.
Okay, but what happens is that it is not in Newton's theory the infinities don't matter because you say that there really is no point particle, but the particles will be slightly extended and so on. In Einstein's theory, what happens is that if there's a singularity in the matter density, because everything is packed at one point, it will mean also there'll be a singularity in the space-time structure. And that is very disastrous. So now the question is whether this singularity is real, meaning is it unavoidable, or is it the singularity has come simply because there is homogeneity and isotropy. One important assumption of standard cosmological models, the universe is homogeneous and it is isotropic. Homogeneous means that it is the same all over. Isotropy means that it is the same in every direction. And if you when you start with a model like this, then within Einstein's theory, the metric is well fixed. The metric meaning the geometry of space-time becomes completely specified except for one function, which is the function of the time. And that function, which is known as the scale factor of the universe, the size of the universe, it's function of time. So as the universe expands, it increases. The form of that can be determined from Einstein's equations. So now the thing is that if I relax this assumption of homogeneity and isotropy,
Okay.
singularity go away.
So that was the
That was the question.
inquiry.
And then there was a group of Russian relativists led by Lifshitz.
Okay.
There's a very famous series of books in theoretical physics called Landau and Lifshitz. Okay, and then Lifshitz, that is the same Lifshitz, E.M. Lifshitz.
Okay.
And he worked with several people for a period of 10 years. And then they claimed that uh, they could have a singularity.
Okay. Even if you
It's
relax
not a
those.
general solution. Okay, so if it is a general solution, then it would mean that it's a big problem. But at that time, in the mid 60s, Hawking and Penrose and Garrosh and others, but mainly Hawking and Penrose, they demonstrated that these singularities are a generic feature of Einstein's theory. They are not based upon the simplifying assumptions which go into the standard model. So there's a big problem. In the Hoyle-Nalika theory of gravitation, which is what is known as a conformally invariant theory, meaning you see that our normal theories obviously they are not dependent upon how big your universe is or how small it is. So if you apply electrodynamics to such certain thing with size, and if the system increases in size, the same electrodynamics will continue to apply. But here you're talking the basic physics, not things like turbulence, okay, which are very dependent on the size. Okay, so now you can consider a transformation in which the size changes, but it changes in different directions and different times in different ways. So, and so they got this conformal invariant theory.
Hmm.
And so it means that there you can keep making this conformal transformation.
Hmm.
And for example, I showed that you can always choose a conformal frame in which specific singularities are not there. So that was the kind of very theoretical work. But while I was doing it, I was also getting interested in astronomy and astrophysics. So for my postdoctoral fellowship, I went to the Institute of Astronomy in Cambridge. And there,
And you work with
Martin Rees,
Sir Martin Rees.
mainly with Professor Andy Fabian, who is a very
Hmm.
famous astronomer.
Okay.
And
Hmm.
then, actually, at that time, there was also the possibility that I would go to Germany, get to work with Professor Jürgen Ehlers, who was a very great relativist. Then I thought that I'll go to Cambridge for 1 year and then to Germany for 1 year. But when I went to Cambridge, I liked it there and I stayed. So then, after that, I started doing astrophysics.
Okay.
Now, occasionally, I do a little bit of relativity now and then, depending on circumstances, but not very much. Now, if I had gone to Germany, of course, then I would have remained.
Okay. So tell us about your postdoc time at the Cambridge. Like, what kind of
No,
problems?
it was a very obviously a very good time in the sense that Cambridge is a very beautiful place, very renowned place,
Hmm.
and all these wonderful colleges there.
Hmm.
And I really did not know anything about Cambridge at that
Hmm.
time.
Hmm.
And Nalika recommended that I should apply for the field fellowship.
Hmm.
And then he wrote to Martin Rees, and Martin Rees agreed to have me there as a postdoctoral fellow if I got the fellowship, which I did.
Okay.
And just before that, I finished my PhD in the late uh, 1978.
Hmm.
79, in the summer of 79, I went to France, to Les Houches. In those days, they used to have these wonderful workshops, long workshops. So this
Hmm.
was 1 month long workshop. And there I met various people and I met Martin Rees.
Hmm.
And then I got to know a little bit more about it. And then when I went to Cambridge, of course, I was at the Institute of Astronomy,
Okay.
which
Hmm.
was a very famous place even then. It was very small at that time.
Hmm.
And computers were just coming in, and I never had to use cards because the first, but then terminals had come in and start, but I did not know any computer programming at all.
Hmm.
Because in those days, theorists like me did not use computers. Now, of course, everybody needs computers for if nothing else for sending email. Of course, now you can do that with your cell phone and
Ah.
sending email, then doing LaTeX. Now you do mathematical calculations using all kinds of things and everything
Hmm. Hmm. Hmm.
works with AI. So now it is totally different.
Yeah. Yeah.
Yes, I've said that I'm not interested in using all these things. But when
Hmm.
I went to Cambridge, I had to.
Hmm.
But it was, you see that the main computers were in the center of the town.
Hmm.
We were a couple of miles away from there.
Hmm.
And what used to happen was that we used to fire off jobs on the computer, and when they got done, we could see the answers on the screen. But the printouts uh, were made there at the computer center. And they were delivered once at around noon and once around 5 o'clock.
Okay.
If you gave a printout, then you have to wait for several hours to actually get it.
Oh, okay.
But Nalika has told me that when he first started using computers for his calculation,
Uh,
early 60s,
hmm.
he actually had to go to London to do the computing.
Oh.
No computers in Kenya.
Mm-hmm. Mm-hmm. Okay.
So it was, and then of course the world's best people came there, and so you must have heard of the Schwarzschild solution.
Yeah.
Karl Schwarzschild was a great German relativist. He died in the First World War, and then his son Martin Schwarzschild also became a famous relativist. And then I met him.
Okay. Okay.
So then, like that, I met Bondi, Gold, and Hoyle, and everybody else. So it was a great place to meet people, and then you make lifelong friendships. I did a lot of work. I started working in X-ray astronomy, which was very much in fashion at that time.
during the end of that postdoc period, what was in your mind? Of course, we know that you came back to India, but what were the options on table?
You see, I had a unusual trajectory. Normally, what happens is that you do two postdocs. In those days, also one was enough. Nowadays, for example, you need to do postdoc for about 5 years and then you start applying. It's always very difficult to get a job. And in my case, what happened was that when I was doing my PhD, Nalikar recommended to me to TIFR for a job.
Okay.
Okay, and then TIFR agreed to that proposal.
Okay, great.
Okay, so when I went on my postdoc, I was on leave from TIFR. But even then, in principle, I could have considered remaining there in Europe and the US. But I mean, I had no urge to do that. I mean, I just thought that this TIFR and I'm going back to TIFR.
Okay. Uh-huh. Tell us about your time after you came back to TIFR, and I think after during that time or maybe after some time, the seeds of IUCAA were,
Yes,
yeah.
TIFR was all right. It's a wonderful place to be in, etc. But I was somehow, I don't see why I should have been, but I was getting a bit bored.
Hmm.
I wanted to do something new.
Hmm.
There was a proposal. There is a joint astrophysics program
Hmm.
in Bangalore,
Ah.
which had just started. It was based in the Indian Institute of Science. It was started in the Indian Institute of Science.
Hmm.
And then Professor Govind Saru, I used to be very much in touch with him. I had a
Hmm.
lot of discussions with him, and he said, can I go there and take charge of that program?
Hmm.
That again would have put my life in a different gear.
Hmm.
But I
Hmm.
thought about it and I said no.
Hmm.
But then in 1987, this
Hmm.
talk of IUCAA started.
Hmm.
And then I told Alika that I'll be very glad to go with him. I mean, it was not called IUCAA or anything like that. It was just said something to do.
Hmm.
I said, regardless of what it is, I'll be very happy to go with him and do it.
Hmm. 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 Okay. Yeah. When we hear the story about IUCAA, of course, I interviewed Professor Abhay Ashtekar. He mentioned about you and Professor Naresh Dadij, right?
Yes.
So tell us about how where you met Professor Naresh Dadij when IUCAA got formed, or you met it
No.
before prior to that?
So what happened was that Naresh is actually
Hmm.
the second last student of the senior Professor Malik.
Hmm. Hmm.
And he worked
Hmm.
with Jain Nalika's father, Vishnu Nalika. So at that time, the senior Nalika had come to Pune as a professor. So that is where Naresh came from Rajasthan.
Yeah.
I think he did his masters in Pilani and then he came there and worked with him. So I first met him because there used to be this conference called there is still go on
Hmm.
IAGRG, Indian Association for General Relativity and Gravitation. Attending those, and I must have met him in one of those meetings first, and then he started visiting TIFR when I was with Nalikar, and then so we got to know each other.
Your own research flourished at IUCAA. I mean, your work spans a vast range from pulsars and quasars to large-scale structure of the universe. For our audience of aspiring students, could you elaborate on one of the key areas?
Yeah, so you see that let's say I did quite a lot of work on galaxies. I worked on quasars, of course, X-ray astronomy, radio astronomy, and all sorts of things. And I wrote a book on quasars.
Hmm.
Nalika and I wrote a book on quasars and active galactic nuclei, which is very well. It's old now. It's more than 20 years old. So
Hmm.
published by Cambridge University Press.
Hmm.
After that, I didn't do much in quasars, and I
Hmm.
started working on because I wanted to do a bit of observational work. So started working on relatively nearby galaxies. So these galaxies they've got a bulge in the center. A galaxy can either be an elliptical galaxy or a spiral galaxy. So then, if it is an elliptical galaxy, it's just a single structure. It's got a certain form. Okay, and it's a three-dimensional ellipsoid, and you see it as an ellipse in the sky. You can see how does the intensity change from the center of the galaxy to the boundary. And galaxies don't have a firm boundary. Right? Gradually, the density of stars will keep decreasing, and it just merges into the intergalactic medium. Right? So and then the way the intensity changes, elliptical galaxy was according to another Divocalus's law, and then there's another law that it changes according to afterwards, which is a generalization of Divocalus's.
Hmm.
And then what happened is that if you now You go to a spiral galaxy like ours, it has got two components. One is a central bulge, and the other is a disk. Bulge is like an elliptical galaxy. The intensity distribution, etc., is like an elliptical galaxy, the bulge.
Okay. Okay.
Disk is rotating around the center. That's why it's called a disk. And then it can have spiral arms. The galaxies in which it's only a bulge and a disk but no spiral arms, then so that is called a lenticular galaxy.
Mm-hmm.
And then once you have got the spiral arm, we call it spiral galaxy. So now we used to look at what is the size of the bulge, what is the size of the disk, what is the importance of the bulge. And then it turns out that there are two kinds of bulges, what are called real bulges and something called pseudo bulges, meaning that
Okay.
the real bulges, I mean, their formation mechanisms are different and their forms are different. So real bulges and pseudo bulges. So we did a lot of work. I worked with a series of students. I myself wrote some programs which will allow you to carry out the analysis of the shape of the galaxy, density distribution. Then the students joined and they did higher versions of that program. So we worked, I think, for 10, 15 years. And
Okay.
now I'm back to working on galaxies from the point of view of using artificial intelligence.
Okay.
Because the galaxies have many features. Because
Mm.
in the disk galaxy can have a bar in it, a lenticular galaxy, a bar-like structure. So you
Okay.
want to know how many galaxies, what fraction of galaxies are bars, where did the bar come from, how old is it, and
Mm.
does it form entirely because of internal dynamics or does it form because of external perturbations also? For which you need to find more and more galaxies with bars. It gets very tiresome, even though now you have got samples of hundreds of millions of galaxies to go through them and see which have got a bar, which don't have a bar. Not a practical matter. So one can train a deep learning network to recognize bars.
Okay.
Then the galaxies can also have other features like there can be large rings inside the galaxies, small rings, large rings. One can freely use AI to do these things, which I do. And so I'm back to galaxies. But for many years now, I've also been doing a lot of work in data, okay, big data,
Big data.
because astronomical data is by definition big data.
Mm.
Right? So, for example, the data that Kepler had,
Mm.
only just some kilobytes if you just put it into it. But for the data, they had to
Mm.
invent logarithms at that time to look at this kind of data. And he
Mm.
established Kepler's laws by looking at the
Mm.
data on the orbit of
Yeah.
Mars. And so I keep showing these things to people that there are the stars at the center of our galaxy, which are going around the galactic center, and you can follow the orbits of the stars. There's a particular star called S2,
Mm-hmm.
which is very, very close to the center of the galaxy. And if you look at its orbit, it is exactly like the orbit of the planet, elliptical.
Oh.
So they first got the data. In the case of Mars, the data was obtained towards the end of the 16th century, the early days of the 17th century by Tycho Brahe.
Mm.
And he gave that data to Kepler, who was his research assistant, to analyze it. And apparently, he thought that Kepler is very bright and he wanted to put him in his place. So he gave him the most difficult data that he had. To Okay, but that was the only data from which these laws could be derived. And Kepler did it. It took him 20 years, but he did it. So now the current version is now there are more and more data. Now there are, when I used to work, the gigabytes of data. Now there are petabytes of data, exabytes of data.
Yeah.
So how do you manage this data? How do you have the system? So something called the virtual observatory. So virtual observatories the concept was born in early 2000s. And then I quickly heard about it.
Yeah.
And then I also had the Virtual Observatory India. I mean, it was a very unorthodox partnership, meaning that I partnered with Persistent Systems,
Mm.
the owner of Persistence.
Mm.
Persistent Systems in Bombay and back in Pune. I have known him since he was the only employee, and he desperately needed email, so he used to come to IUCAA, which was in a shed at the time, to send email.
Mm. Mm. Mm.
Because we are the only people outside of Bombay who had email. And then so he used to come, and then that developed into a friendship which went into these scientific projects. So when I
Mm.
wanted to do this big virtual observatory projects, I approached him and he said he will support me and he gave me 6 engineers free of charge. And that was 2% of his workforce at that time because he had 300 people. They thought
Mm.
it was a big company.
Mm.
So I was telling them that if they now gave me 2% of their workforce, they would have to give me 600 people because they are close to 30,000 people, I believe.
Oh, okay.
So it went, and then from virtual observatory, then I had a big data project from when Dr. Chidambaram was the principal scientific advisor.
Hmm.
The PSA has got a small amount of discretionary funds. So he gave me funds to carry out a big data project, which I did towards the end, just as I was retiring.
Hmm.
So, but of course, now I still continue with all these projects. But now, so there was big data, there was computer visualization and all those things, and then all the graphics. How do you download large amounts of data and how do you work them? But now it is all everything. The focus is on AI now, and as you use astronomy, so we can use it on images, we can use it on spectral data.
Hmm.
So,
Yeah.
and then there are two ways of using AI in astronomy. So one way is that let us say that you want to solve an astronomical problem. For example, we wanted to look at stellar spectra and classify them. There's a standard classification available for stellar spectra. We can classify these stellar spectra using AI.
Hmm.
And we did not. There are some technical issues which come when you do that, and we did not know how to get out of those.
Okay.
And it was recommended to us by an expert. Use autoencoders.
Okay.
Okay, so the thing is that there we were solving this problem of spectral classification, and we used whatever was needed to solve it, which are autoencoders.
Hmm.
Okay, autoencoders, of course, now are extremely famous.
Hmm.
They are used in all the generative AI, etc.
Hmm.
Other way of doing this, and I use a combination of both these ways.
Okay.
One is continue to do what you to solve problems using the simplest AI applications. And the other one is where you say that, look, my God, this is a very profound new AI development. How can I use it to address
Hmm.
astronomical questions? So, for example, if you take large language models,
Hmm.
then and all these things with people, or everybody uses ChatGPT.
Yeah.
What are large language models? And what are large language models based on? They are based on something which is known as attention mechanism.
Hmm.
The attention that there is transformers.
Hmm.
And so there was a beautiful paper written by 8 authors in Google, two of whom are Indian.
Yeah.
And one of them, she did her degree from a college in Pune.
Okay.
Okay, and there's nothing. I mean, it's a well-known institute, but there's no AI specialization or anything. When they wrote this paper,
Oh.
which has 150,000 citations on last. So and that is completely. I mean, that changed the whole course of AI.
Hmm. Hmm.
So that is things are, and so you see the point is that they provide you a mechanism because when you are when you want to parse a sentence,
Hmm.
you've got all these words, one word following the other.
Yeah.
But a word that you are reading now could be related to a word which was 100 words before. So how do
Yeah.
you maintain that correlation? So now you see that the idea that the words are in a sequence,
Hmm.
but a spectrum is also in a sequence. You see, because
Hmm.
you've got a wavelength and you've got intensity. You can't interchange those. It has to be that sequence. Similarly, at the time data also, time what's called timing data, meaning that I'm looking at observing an astronomical object which varies in time. So I got intensity of the object as a function of the time. So these create a time series. Okay, so these kind of data again are amenable to transformers. So there you say that look, I mean, I got this wonderful technique. Let me try to apply. So we use both of these. It becomes very challenging.
Okay. That's great actually, and the use of application of AI, and of course, I mean that would speed up a lot of manual work also.
Yes, that's because, see, the thing is that now your data is in billions of galaxies, hundreds of millions of galaxies. So you really, and it is not, there's no point in just studying identical spirals. And you study 100, then you got 1,000 is enough. So if you similar objects are not going to, you really want to look at unusual objects, you want to see things that are different. So for that, you have to look at a lot of objects
Yeah.
to decide what is mainline and what is unusual. So that can be done wonderfully well by AI.
Yeah. Yeah. Identifying all those outliers and then classifying them possibly.
So we are now working on a problem which involves looking at X-ray spectra to decide whether the underlying object is a black hole or a neutron star.
Mm.
So I worked with a intern on it 5 years ago, and we wrote a nice paper on it. Then we had the simplest thing that we use what was random forest. Okay, so now we are using deep learning techniques, and we are getting very interesting results. The problem is that when you look at all these spectra, see, if you look at a stellar spectrum, then it has got all these absorption lines in it, and sometimes emission lines, but mainly absorption lines. And by looking at those, you can decide what is the classification, and it is obvious to you. If you show it to an astronomer, trained astronomer, they can just
Mm.
look at the spectrum and say to you what type of star it is. Is it O
Type.
or M5 or what? So people are looking at it for a fraction of a second. Problem is that if you've got 100 million stars, even if you look at it for 1 second per star,
Yeah.
so it was 30 years of work.
Yeah. Yeah. Yeah.
On the other hand, if you look at the X-ray spectra,
Mm.
you look at it and you don't see any features in them.
Mm.
So you as an observer, as a human being, cannot say which of that is a black hole and which is a neutron.
Neutron star.
But the AI system can do it. Okay, so the question is, what is it that the AI is seeing that you are not being able to say? And that kind of a question, pose it like that, then you are entering the realm of explainable AI. Okay, what happens in explainable AI? That you have got this kind of a solution. You have got you have built a system which does what you want to do. You want to know how it is doing it. Because this kind of a spectrum that you see, it comes from different kinds of components. It can come from an accretion disk, from the corona of the accretion disk. It can
Mm-hmm.
come very close to the black hole.
Okay.
Okay, so we know we have got fairly good idea of what are the different things which make a contribution. Okay, and you can use those to synthesize this spectrum.
Mm.
Okay, but then here, because the resolution is not enough, not uh, you're not able to see these different features, but the system is looking at it. So if we're able to explain it, then we'll also be get an insight on which are the underlying astrophysical processes which are producing this spectrum.
Okay. Okay.
So
That's
that is
fascinating.
going on. We are just writing a paper on that right now.
Okay. Okay. Oh, wonderful. That's fascinating.
No,
So many of our students are like high school students, and now you know that AI, especially you mentioned about say ChatGPT and all, those kind of large language model and other AI systems. And now students are aware about this; they are using these, right? And so in India, an Indian student who is in grade 11 and 12 and want to use data from virtual observatory, what would you propose that student, like? How do they go about it? Like, how
see,
do they
now
take part in this
what I find is that young students have this amazing knack to work with laptops and
technology?
things. So, for example, if you take a 4 or 5 year old student,
Hmm.
they can do a cell phone very well.
Hmm.
They take to it just like that. By the time they are 10 years old, they are teaching their parents how to do things.
Yeah.
And I have grandchildren of that age, and they are pretty very adept at these things.
Hmm.
It is a great mystery to me for the following reason. See, they are adopting to it extremely fast. The other thing that they don't adopt. Okay, so why? What is it? You see, when so it is an inbuilt ability
Hmm.
to something, and that ability resonates with the IT devices.
Yeah.
So what is that item? What was that thing provided for?
Hmm.
And it is not that there are two exceptional children in the whole of the world who are doing it, because then they say they are freaks. Every child can do it.
Yeah.
Completely uneducated children can do it. So there is that inbuilt ability. And
Hmm.
what is it is the question.
Hmm.
So now I find that if you take the youngest people who are working with me now are
Hmm.
53, 54 years younger than me. And then they are trained themselves to use these things, and all the AI techniques. And
Hmm.
you see, the thing is that if I tell you about transformers,
Hmm.
if you want to understand what is a transformer, it
Hmm.
takes a great deal of effort. But if you know that transformers can be used to analyze your data, and if I give the data, because there are all these wonderful systems which do the work very easily for you, right? There are all these AI systems.
Yeah.
which will do that for you. So if you know, you need to know Python programming,
Yeah.
which is trivial for a high school student to learn.
Hmm.
Okay, then in the old days, they would require somebody like me to tell them that there's a thing called virtual observatory. Here, as soon as they hear about that astronomical data, so they have to ask, okay, where is the astronomical data available? And they'll be led into that. And most of these databases come with absolutely excellent packages for the data analysis. So without just by having this, when in the old days I used to go to the library and read books,
Hmm.
but I couldn't ask any questions to anybody. Here you can just ask a question to ChatGPT for it.
Yeah.
So all these facilities are there, and they are able to use them for some amazing reason.
Hmm. Yeah.
That doesn't mean that they have the maturity. They don't understand what is going on. So even my postdoctoral fellows and these young students who are very clever with it, they come out with all the results. Okay, plot a graph, and then they'll bring something and which looks like a rectangle. I said that this is not. Why is it looking like a rectangle? Because it should be a chi-square distribution. So then I have to point out to them that look, you are using the wrong scale. So use the correct scale on the axis, and then immediately everything comes out.
Uh,
And then the interpretation, what is it? All that takes a long experience. But the
Absolutely.
ability, so you ask me how could young high school students use it? They just said, okay, there's something called a Sloan Digital Sky Survey. So just put Sloan Digital Sky Survey into the internet,
Hmm.
and then you'll be quickly led to it.
Yeah, and download. There's a lot of data available
Yeah,
out.
there's a lot of not only data is available, but there's also systems for analyzing the data. There are
Hmm.
all kinds of examples. And then you can do quite a lot of computation in situ. You don't have to do it on your own. You're unlikely to have access to expensive computing.
Hmm.
Much of the computing can be done on their side.
On their servers, basically.
So all that you need is there.
Yeah, absolutely. That's quite fascinating, sir.